Today I'm in a series of lectures we are going to study together mesoscopic quantum electrodynamics, which is related very strongly to what Jason has talked to you about. In fact, in this lecture you will have some kind of a déjà vu feeling between the lecture of Jason and the lecture of John Hatton, at least for the beginning. There might be some overlap, but at the same time there will be things which will be different, and therefore it's good to start really from the beginning and to establish a common vocabulary about these mesoscopic quantum electrodynamics. So again, it's this. So the systems which we'll be dealing with is essentially mesoscopic systems which are embedded to microwave cavities, but like the general ideas which we will develop are not restricted to microwaves depending on the energy scales. And essentially the idea is that we will have some kind of mesoscopic circuit, so which I can sketch like that. So I have some kind of contact here. So I have a mesoscopic region, and then I have another, I can have several contacts, in fact. I mean, I would something like this. So usually you have some reservoirs. You can, let's say, bias this reservoir with a battery here, and look at the current flowing here and here, for example. So this is a mesoscopic, a generic mesoscopic circuit. And here you will have some reservoirs. And in fact, usually, very often, I mean, in the field of mesoscopic physics, what people do is to study the transport, so the current as a function of all the external parameters flowing through that kind of device at the current at low frequency, as a function of the bias here, as a function of the extramagnetic field. There are some control knobs also, so I can have some gate here, etc. And what we're going to do is to see whether it's interesting and well, in fact, I hope to convince you that it's going to be interesting, whether it's interesting to embed this kind of system into a cavity like that. So there's one mirror of the cavity. There is another mirror of the cavity here. And essentially, the idea is to study. Now there will be photons traveling back and forth here. And so the idea is to see some interaction between this guy and this guy here. So for example, a coherent interaction, but not only. And we'll try to see whether it's interesting and what we can learn from the interaction between these two systems. We will focus on microwave cavities. But like the general, I mean, ideas are not restricted to that, as I said, microwave cavities. And why, I mean, why essentially it's interesting to couple this guy to microwave cavities? It's because many of the energy scales which in fact occur in these kind of systems are actually the microwave range. So for example, if I take a very so one very much studied system in mesoscopic physics, which is a quantum dot. So it's a quantum dot. It's like this. So you have a coupling to the left, coupling to the right. Then you have a bias here. So you can put a battery like this. And then there is this energy level epsilon d. And essentially, there are two things which can happen, which can, two energy scales at least, which can lie into the microwave range. First of all, the gammas. So okay, the gammas, it can be essentially, it can be like, they can vary by many orders of magnitude, but that they can be as high as about 10 gigahertz, 10 to 100 gigahertz. So if we really open the contact, so there is one energy scale which is definitely in the microwave range. And for example, I mean, if I apply now a magnetic field in the system, so I will split the energy levels. I will spin up and spin down. And if I have a G factor of 2, and I apply 500 millitesla on the dot, this will lead to a spin splitting, to Zeeman splitting of about 14 gigahertz. So you see there are at least 2 energy scales which are in the microwave range. And you can do essentially, so this is for quantum dots. Of course, there are many other energy scales. So there is the hyperfine coupling, there is like the spin-orbital interaction also. So which might give you a hyperfine coupling. Spin-orbit interaction. So they also can lead to energy scales in the microwave range. Although it's not as obvious. I mean, there are like, but this can be also in the microwave range. Okay. So, but this is not restricted to quantum dots. Of course, quantum dots in cavities, as Jason has already shown to you, are very important applications for mesoscopic quantum electrodynamics. But let's say if you consider a diffusive wire, for example, so a mesoscopic diffusive wire. So this is quantum dot. And of course, yeah, so this is a single quantum dot, by the way. And of course, one particularly important regime is the regime of a double quantum dot, which we will study a bit at the end of the lecture, maybe this afternoon. And of course, which is what Jason has talked to you about. But there is another very important mesoscopic system, which has energy scales a priori which lie in the microwave range. So this is a diffusive wire. So let's consider now that you have some, again, reservoirs. So you have a diffusive wire. So they have some disorder in the diffusive wire. And let's say now I have a length here, L, which is 1 micron. So this is so in that kind of system, of course, you can have coherent phenomena occurring. And here, like the very basic very basic energy scale is related to the diffusion time. So if D is the diffusion constant, so which is like in 3D, so 1/3 of the Fermi velocity times the elastic mean free path. Essentially, there will be a diffusion time, which is L square over the diffusion constant. And so this gives, of course, the Thales energy, which is the energy scale, Thales energy, which is h bar d over L square. And this diffusion time, if you take like standard Fermi velocity, so for example, I took, 10 to the 6 meter per second, and so if you take 10 to the 6 meter per second, and you take elastic mean free path of about 10 nanometers, you end up with an energy scale which with a frequency which is so h over tau, which is about 3 gigahertz. So you see again now, like the Thales energy or the inverse diffusion time lies also very quickly. I mean, very like in a very generic situation in a microwave range. So, although of course, I mean, okay, this is like the microwave range defined in the range between 1 gigahertz and 100 gigahertz. Let's say, like there is no, I mean, hard frontiers. And yeah. So, well, this is one way of measuring directly the diffusion time. But for example, if you look at if now you attach a superconducting electrode here, the Thales energy directly shows up in the spectroscopy of the system. So, and therefore you can directly have, I mean, the correlation functions are related to the Thales energy, which is h bar over the diffusion time. So, but one way of measuring, in fact, that's the point. One way of measuring directly the diffusion time and also the relaxation processes in that kind of system is to couple it to the microwaves. Well, no, but it's just that here, I mean, you will have an access directly on the dynamics which are related to this diffusion time. That's why I say directly. Okay, the wording directly, it's okay. Well, maybe I should not use the word directly. Okay. So, but there is another very important energy scale which is actually tunable. If you have a, so now I take another, I take another system which is even simpler in a way. I take a tunnel junction. So it's okay. It's not really mesoscopic, strictly speaking, but although I mean, of course, the insulating barrier here is nanoscopic. I take a tunnel junction. And here, well, in fact, I mean, I have to, so let's say, well, this is true, in fact, for any kind of central conductor. This is an insulator here. But I mean, this is also a generic situation, which would be, again, with barriers. So you have a mesoscopic region. And now you have some bias here. You see, I put the Fermi C is not exactly, and essentially, so essentially now, okay, you have Fermi functions here for the occupation, and the measurements are carried out at low temperatures. So which means that there is some width which is about 3.5 kBT. And let's say if you are at about 50 millikelvin, I switched the, you are at 50 millikelvin. So this would correspond to a kBT of about 4.3 micro eV. So which are like, it is about 1 gigahertz. And which means that now any bias which will be larger than that will give you a natural energy scale, which will be also in the microwave range. So now if I apply a bias, which is, so this bias here, let's say I have a battery here. And so now for large bias, for bias larger than kBT, because of course we want to have well-defined energy scales. In fact, you can have a bias in the microwave range. And so this is going to be important, for example, if you want to study emission processes, as Jason mentioned, but also, for example, there are many people working with superconducting, with essentially tunnel junctions with superconductors on both sides, and by applying a bias which lies in the microwave range, I mean, they can couple resonantly to the microwaves. So you see, there are many energy scales and processes which are in the microwave range, and so this is why, I mean, experimentally, it's interesting to try to couple these systems to microwave resonators or cavities. Okay, but now we can do essentially the same, like follow a similar reasoning for how to make the microwave cavities, and see what kind of energy scale shows up and what are the relevant lengths which are important in the microwave cavities. So there is one way, I mean, to make these cavities, but there are many other ways. So I just take my favorite one. So it's a Coplanar waveguide cavity. So now we have defined more or less what we will be talking about for generic mesoscopic systems. So you see that you can combine, I mean, you have a wide variety of possible combinations. And now I have to specify better what is the essentially or what will be the microwave resonator. So I have a Coplanar waveguide cavity, which looks a bit like that. So you have a ground plane here. So you have some kind of launching pad. You have another ground plane here. So this is not. And then you have a central conductor. Okay, and so this has a length here now. So I will take a different, yeah, okay. I mix the notations. So these are my mirrors. These are the mirrors of the cavity here. So the mirrors are in fact are cuts in the central conductor of the cavity. And now if you take a cavity which is, so if you take this distance now, which is about 10 millimeters, so you see this is a macroscopic distance as compared to essentially the fundamental frequency of the cavity will be C over, so 2L times the square root of the effective permittivity, and this is about 6.4 gigahertz. If I take the effective epsilon for that kind of geometry of 5.5, which is what we have for our substrates of silicon dioxide. So this is typical. It depends, of course, on the mode geometry, and this is typical. So you see how now to make, but this is one way of making microwave cavities. There are many other ways, but this is one way which I like particularly. And so you see that now this there is a mesoscopic object here, which we are going to couple to a macroscopic object, essentially, because it's 10 millimeter long. And actually, I will show you that this can be can lead to a very large coupling. And so, just another thing which is important is that the quality factor, so which relate to the line width of the cavity, which is about, I mean, in a range. So, typically for a mesoscopic QED, it's in a range of 1,000 to 20,000, essentially, something like that. Well, it can be even larger. Okay, so now there will be two ideas. So the ideas behind this behind the mesoscopic QED is the first is which is coupling mesoscope. So mesoscopic circuits, two microwave resonators. So the first idea is, of course, related to quantum information processing. So is to use the tools of Cavity-QED to manipulate couple and read out so individual electronics excitations. Okay. Or electronic degrees of freedom, or electronic degrees of freedom. In closed systems. Well, that's the first idea. So there is the spin, which we have just mentioned. There is the orbital degree of freedom. So this is very much, I mean, what Jason told you, I mean, also in his lectures. There are many other degrees of freedom. So we can have also Cooper pairs if we have superconductors, etc. So this is one idea, but the second idea is to say, but this might be a powerful tool. So it's the use of cavities as a powerful tool to essentially probe with a very high sensitivity these kind of systems, in which, of course, you can have transport, so out of equilibrium phenomena. And also you can have strong correlations between the electrons. So use the cavities as a very sensitive probe. Of so transport generally, so out of equilibrium phenomena. So correlations, electronic correlations. And also, I mean, exotic. So we can have also. So we also want to do some exotic things. So exotic excitations. Okay. So and so, like generally, these things will be more in the open quantum system regime. So open systems. Meaning that essentially now, for example, for quantum dots in this regime, the gammas will be large essentially. Okay, so now that I have introduced the relevant energy scales, we will essentially try to see how to describe like properly these two limiting cases in a single, I mean, in a single way, essentially. And essentially most of the material, so by all this, I mean, is actually going to appear in a review by Audrey Cottet and so et al. In the Journal of Physics condensed matter. And also, I mean, so I can give you some other references also for more, I mean, even more detailed references. So, so now, and then we start with the description of these systems. Yeah, so I didn't want to tell this right from the beginning, but for exotic states, I mean, these days, okay, there are many exotic excitations which are related to topological metric. So in fact, at the end, I will show you a specific example how to use, in fact, these cavities to probe Majorana excitations. Yeah, so that's, so don't leave, I mean, stay till the end because there will be some Majoranas at the end. So, but there are many interesting things, I mean, besides and before, I mean, I hope, so okay. I hope that you will not come back just for the end, but stay till the end. So there will be many other interesting things, don't worry, hopefully. Okay, so yes, so you can look, I mean, I think it's going to appear, I mean, like in the coming weeks. Okay, so now we start again. So we had this several times already in this week. So we start with the generic description of the Cavity-QED. So in our case, we like to have a second quantized form of the Hamiltonian. So I have, let's say, the one-body Hamiltonian. So this is the hat here, plus the Coulomb term, plus so I just assume that I have only a single mode of the electromagnetic field. So I don't want to get into the n plus best here, yeah. So because of course we want to measure these things. And so the photonic mode, I mean, is attached to that. So there are two things which I would like to say. So I assume that I have done the job of quantization of the electromagnetic field. And so if you're interested, you can look more in this. And also there is an Audrey Cottet et al. It's a PRB. Because it's it's not exactly the usual way of quantization of the electromagnetic field. So it's there is some variation with respect to the usual, let's say, textbook examples. And so I assume that you have done a job of quantization the electromagnetic field. So this is why I have written down now the cavity part like that. And I specify, I mean, I just focus on the single mode because this is exactly what we're going to do experimentally after. So I have a single mode of the electromagnetic field, which is characterized by these photonic operators. And essentially, so the Coulomb part, so we'll have the generic form. So like that. So there is a prefactor here. I don't specify that. So the Coulomb part, and so the it's E square. That's the Coulomb, the generic Coulomb kernel here. Coulomb interaction. This is more, let's say, the static part of the Coulomb interaction. And then the most important thing is that now the one body, so all the coupling, let's say, which stems essentially from a gauge invariance argument to the electromagnetic field, comes, I mean, exactly like we saw from the kinetic term of the plus from the vector potential here. So minus so two potential. So there is one potential which comes from the harmonic mode, which show up in the in the quantization process, and there is the confinement also. And so I specify now the form of the vector potential, which is some function A of R times the usual quantized form of this quadrature of the electromagnetic field, which is like that. Okay. Sorry? It's essentially it's just a scalar potential which comes from the interaction of there is an additional static part. I mean, which comes from the fact that there are some modes. So usually, what you do when you quantize the electromagnetic field, you essentially divide into transverse and longitudinal modes. But since you have interaction with this with this density, with this mesoscopic system, with more general electronic density, essentially you have also other modes which also are neither longitudinal nor transverse. And when you essentially write them down properly, you find that they correspond to an additional shift in the scalar potential. Exactly, yeah, exactly. Yeah, this is the ionic part. This is the confinement, so generic ionic part, exactly. And so now I will do a basic assumption here, which is rather, common, is that there is only a coupling to the electric part, there is a coupling to the electric field only. So in our case, this is kind of rather reasonable because the magnetic coupling for individual charges, so the magnetic coupling for a single spin, for example, is about 10 hertz. And so whereas what you will see is that the electric coupling will be in the range of the megahertz, in several tens of megahertz. Okay, and therefore, and then of course I assume that I have no loops in the circuit. Okay, and under these assumptions, which are pretty generic, I mean, there are many examples which are essentially which fall in, which don't have this. Essentially, I can write down that now the direct product, the rotational of the vector potential is roughly 0, and then define a transverse field here. So it's like this. A transverse potential, which will give essentially the part here of the. So essentially, I go back to some kind of potential, and now using this assumption, essentially we can write down. So this resembles essentially the usual dipole approximation, although it's not fully the equivalent to the dipole approximation. It goes beyond, as you will see. So now, I have this here. This is important. And now, essentially, what I will do is to write down. So because here you see there is this. So this is P. This is A. There is this square term which we heard about yesterday, and so we would like to get rid of the square term to have a more handy way. Of dealing with the Hamiltonian, and so we will write an effective Hamiltonian by doing a unitary transformation. Well, it's not really an effective Hamiltonian because this unitary transformation, in fact, is exact. And so we will essentially use as an operator here to do this change, essentially, of this unitary transformation. An operator which looks like that. So it's over h bar naught, yeah. Times here the integral here of and normally there's, yes, exactly, yeah. And so you see that here this looks like so you see this looks like some kind of displacement operator for the photonic field, because you have the electronic density here with the coupling term. And this guy essentially will shift the operators. So he will shift essentially the electric part. And so you can now write down, I mean, essentially the so I will essentially using so this unitary transformation here. So you will end up with with an effective Hamiltonian, which now is more, I mean, handy. So there will be a h naught here. Now I say that this is what we call this is a photonic pseudopotential. And essentially now this photonic pseudopotential, you will see why we call it photonic pseudopotential. It's because in fact it comes here as a linear term coupling to the other quadrature of the electromagnetic field. So this is the electric potential here. So the electric potential, or the electric field. So there is still the h bar naught here, plus the Baths. And now now h naught here is the same as before, but without the it's the same as before. So it's still but with the h tilde here, with now all the same terms, except that there is no, I mean, the vector potential has disappeared from the kinetic term. By the way, in fact, we can also add up an extra term here if we want to treat superconducting systems. We just have to write the gauge invariant superconducting pair potential here, and essentially with exactly the same transformation works, and then you have everything in there. Okay, so now you see that now this term here. So that's the important part here. That's the important part. So this term has, of course, so this is what this would be V, the potential. And this is something which depends. You see, there is a coupling term here. So I just put quotes because for the moment it depends on the space coordinates, but there is a very simple, essentially, interpretation of this guy, is that inside, I mean, you have the coupling times the density, and essentially this term is a rho v like, I mean, term. So it's a coupling between the density and the electric potential. So this is very, so we started more or less with, let's say, what we could call the magnetic part, but in fact, it turns out that we can turn into an electric field here, which is, and therefore we end up with the let's say with the density. So density potential coupling. So the density of the. So here I have not specified where is this density here. It's anything in a conductor, in fact. Okay. And so now I will apply this to two important limiting cases. Yeah, sorry. V perpendicular is the scalar potential which derives, which allows us, whose gradient is the vector potential, because we have assumed pure electrical coupling, and therefore that this part has no rotational here. So this is the usual assumption here. So we assume that the vector potential derives from a scalar potential. Okay, because we are in the electrical coupling scheme essentially, and therefore we assume that the magnetic coupling, because we're going to be coupling to single spins, so this is way smaller than the coupling which we will measure later on, and there are no loops in the circuit. In mesoscopic circuits, you can have loops, but here we assume that we will leave this for the moment. Okay, and so now there are two important things which we can have. So there are two important limiting cases. So the first limiting case, so I write down again here. So the pseudo so there is this coupling term here, this V. So it's minus. The special integral here of this V perpendicular times the density. And so there is one important limiting case, is the case of Cavity-QED, where essentially the electric field is more or less, constant at the scale of the density, which is important for coupling to electromagnetic field, like in the simplest cases. And essentially, you can approximate this guy by R. So you say this is more or less R scalar E naught, where is the electric field. And therefore, there is a very simple form which many people, of course, already know. So you have something which is here essentially the dipole. Here you have the R plus the electron times you have the special integral of R times the electronic density. So this is the electric dipole, which is and so this is the usual D dot E, let's say, picture, or I don't know, so yeah, picture or coupling scheme of atomic physics. But as you will see, so this thing, well, is okay. It's a sanity check. But what we would like to do is to apply this to mesoscopic circuits which have very inhomogeneous potentials, because this is what we do for engineering a coupling experimentally to that part or the other part of the circuit. And so I will show you that now we can reach with circuit-QED, but something more general than just circuit-QED with the mesoscopic, with the superconducting circuits. And so I have three examples now. Oops. And essentially, Yeah, so now I will define a generic structure which will be something like that. So again, I have some reservoirs, so I have tunnel junctions now. So I said I have some kind of dots here, but of course the dots which I sketch here can be sites, for the discretized version of this of a specific device. So I can have something like that, something like this, for example. I can have a structure which is like this, and then I will define essentially the orbitals on these different parts of the circuit. So I have a coarse-grained approach to the. I will say that for each node, I can define a constant, essentially more or less. I mean, a region where the field doesn't vary so much, and where I can define the orbital wave functions. And so, which means that here I will have so I, j. I mean, I will have some nodes, and therefore I will expand the field operators on these nodes. So expansion. So j are the nodes of the circuit. And so therefore, what will happen is that there will be, so now you can completely expand, I mean, all this, I mean, now you can plug in this guy in there. And so you will have essentially now for nu here, a very simple form. I forgot the charge here, in fact. So there is a charge here, yeah. And so, okay, then I have, of course, I mean, I can do the expansion, and so I can, and then, of course, in this now, there will be a diagonal term, so which I have, which is like this, and there will be some kind of cross terms, which will be, so I will call gamma here. Oops, and there is C, J prime, sorry. And so the very important thing is that this G now is just the average of the transverse part of the photonic field over the orbital, over each orbital wave function. And this guy here is some cross term. Here is the overlap. Times and so this is just expectation value of the field here. This is some overlap. So usually this one is much smaller, although it can be important in some cases than diagonal. So we disregard it for the moment, this term here. And so all this thing is just to establish, I mean, so and now I will show you that like what I think to be the three important cases for three important cases now. So we can apply this now to three important cases. So a single dot is just that you have a single orbital. So you have so the orbit, you have an orbital which is characterized by the operator d or d dagger. And therefore, I mean, now this guy, I mean, is just so the coupling term, so which is will just be now G. So so d dagger d times A plus A dagger. So again, I mean, so this is just So I omit the spin indices here, but so this is just the total charge here of the on the dot here. So it's so now I can have also the double dot. So this is another very important case. So the double quantum dot. And you see that now, I mean, depending on the orbital, this expectation value is not necessarily the same because it's related to how much the wave function of the left and the right dot, I mean, is affected by the electromagnetic field. And so now, I mean, the coupling term, I mean, it's, so this reminds you of what Jason has, so now I have two orbitals, the left and the right orbital. So left, it's C dagger L, C dagger CR, and then and so now there is again a very simple form. And which is again, I mean, as times so you see this is very intuitive. I mean, the of course that's very intuitive what we obtain, which is somehow, I mean, nice. But it's important to start, I mean, from more microscopic grounds, because then if you write things like that right away, I mean, you can think, for example, that you can mix, for example, this kind of term with, depending on the way you couple the mesoscopic system to your device. So it's important really to know that you don't forget. I mean, you don't miss any coupling of this of the electromagnetic field to your mesoscopic circuit, and therefore this is why it's important to start really from scratch to be sure that you don't omit any term, any coupling term. And then one other very important is when you have, for example, a single dot or a single, well, let's say a single dot, let's say, plus left-right reservoirs. This is going to be very important, for example, if you want to drive out of equilibrium, I mean, to drive this, the thing out of equilibrium. And so in this case, I mean, again, so now, so we have the similar term, so which is, so again, and if I say that now they have electronic orbitals of k vector in the left and the right reservoir, so the left reservoir and the right reservoir, then what you have is that you have a sum here of G, I mean, left K times C dagger K C K plus G right K here. And so this means that this guy now renormalizes the chemical potential. So there is so this means that now so if I sketch now what is going on, so I have the Fermi now C, I have the and therefore and so I have like gamma left, gamma right. And now, I mean, the electromagnetic field, the cavity field can do several things to the dot. It can, of course, shake now this guy. So this is the coupling term G, but it can also shake these guys. So this would be G sum over K over G left K. And it can shake also this guy. So sum over K. And so this is very important because now you see that the field can shake, of course, the gate, but it can also shake, for example, asymmetrically the source and the drain electrodes. and this can be very important for understanding experiments, and also for maybe proposing experiments. Okay, so you see that in a way, so this approach allows to bridge, between Cavity-QED and Circuit-QED with some specific, let's say, some specificities for, let's say, mesoscopic circuits, which are not superconducting circuits, in which essentially for superconducting circuits you have only this term, which modifies which is n being now the number of Cooper pairs in the superconducting island, and this is only this term which plays a role. And now we have a whole wealth of other coupling terms to the electromagnetic field, which can be interesting. Okay, and so now again, since I will show you experiments, it's important to have a notion of the order of magnitude of these terms. Yeah. Absolutely, yeah. Exactly, yeah. Exactly. So here I haven't done any, special assumption of the field operators right from the beginning. So this is all the charges interacting with the electromagnetic field. So the electrons from the leads, and from the yeah. So then this is microwave engineering. So I will show you in an example of my experiments how you can suppress this coupling to the leads and have only a coupling to the gate. Yeah. Okay. Okay. So now it's good to have an order of magnitude. And so for the order of magnitude, so essentially, what I will so it's good to have an order of magnitude. Let's say for this coupling term, but this is the same for all the like we get similar figures for all the other coupling terms which I have written down here. So essentially, I start again with the G here now. So I put the H bar now. So H bar G. Now, so you see there is the expectation value of the wave function on the electric part of the electromagnetic field, which means that this is going to be a capacitive ratio, which is so I will write down like this. So it's alpha, and it's V RMS, which is what is hidden essentially in this curly alpha here. There is the vacuum, fluctuations of the electromagnetic field, and so this is the capacitive ratio. And the capacitive ratio, it's okay. It's something which is it's around 0.2, 0.1, let's say, something like this. And now the VRMS, so if I have this kind of Coplanar waveguide resonator, so essentially it will have a simple, a simple form here, which is essentially H bar omega cavity over so the capacitance of the resonator. There is a factor of 2 normally. Yeah. And so, okay, this is not very handy. So I like personally to have another way because I like to deal with impedances. So I can rewrite this like that. So it's a pi. So it's the impedance, the characteristic impedance of the line over so the quantum of resistance. So this is the square root of L resonator over C resonator. And so you see that now, so this guy, so it's about 25 kilo ohm. And this guy now is about, in conventional setups, is about 50 ohm. And so knowing that now, I mean, this guy is going to be going to correspond to 10 gigahertz, essentially I can immediately see, well, immediately not, but I mean, if you can, if you write essentially this gives an order of magnitude with that kind of capacity ratio of 100 megahertz. So of course, I mean, so okay, so this is, so you get the large, so 100 megahertz is if it can be, for example, larger than some relaxation or dissipation mechanisms in so I put it in red here. So it's a large coupling strength here. So we have large electrical dipoles, and this is normal because we have a mesoscopic system. So the dipole, which is corresponds to this to the charge moving over this mesoscopic length, it can be very large, and so we have an impedance here. I mean, a picture which allows us to estimate with this or that impedance how, I mean, you could how it depends on the impedance here. And so for 50 ohm, it gets this. Of course, if you increase now the impedance, the characteristic impedance of your line, then of course this can blow up and increase even more. This can be interesting to enhance the light matter coupling. Okay, and so now what I will do, I'm not sure I will have time to, but we will continue this afternoon, is now we'll apply these things to two very important situations. So the first important situation is a single quantum dot, so which are related to experiments which are being carried out, of course. So so the first situation is a single quantum dot. So two examples, two important examples. So there will be two important examples. So the first is a single quantum dot. So the single, I sketch it. So I just will specialize to the case where essentially I have one hard wall here and only one, so one level here. So a single quantum dot. So you see that here, this is a situation where there is actually no transport in the device because there is only one contact and one hard wall, and so you will see that the cavities allows you to address that kind of situation, whereas in a conventional transport setup, you will not be able to tell anything unless you have some charge detectors, etc. But and then there is the other very important example, which has already been let's say studied a lot. I mean, in lecture, I mean by Jason, is the double quantum dots. So this will be the second part. Maybe we'll go faster on this. So which is something like this. So I have epsilon left and epsilon right. I have a coupling here between the left and right, which is T, and then these couplings here, we will put it to very, very weak. Okay. Okay, so now essentially, no, and then everything will be in a cavity. So this will be in a cavity. So this is one example, and the other example will be this also in a cavity. So the reservoirs also, in principle, will be in a cavity, because as you have seen, the cavities are macroscopic objects, so it's difficult to pull out these reservoirs from the cavity. It's in fact impossible. The leads are always in a cavity, and so you can make use of the leads like in Jason's experiments. But in this case, it's equivalent to a coupling to the gates, and you can also make use of the direct coupling also to the left and right, and try to minimize as much as we can the coupling to the leads. Okay. And so essentially. Well, essentially, I will stop here because there are still 2 minutes left. We will go faster. And then this afternoon, this afternoon there will be you will know, I mean, the answer for the single dot and for the double quantum dot, and we will immediately apply to some specific experiments. I will show you experiments. So we'll go faster. And then I will show you specific experiments where we can, with this very simple, I mean, let's say this this picture here, I mean, will be very efficient to understand essentially the experiments in both situations. Okay, I thank you for your attention.
There are the further questions, yeah.
So, can you explain in the circuit-QED diagram, why did you expand the phi r, the chi dagger r in such a way?
Yeah, this here.
This expansion?
No, but this is the conventional, expansion of a field array. So you have you define orbitals in your you define electronic orbitals, and so you assume that it's a kind of a tunnel Hamiltonian approach. So you forget about what is going on in the barriers, and you say that I have only sites with orbitals here in all the nodes and orbitals in the electrons, and this is the conventional expansion of a field operator when you say that you have a set of a complete basis for all the particles in your system. It's just that here there is I use the usual trick that in the tunnel Hamiltonian picture I forget about what is going on there, and in principle this is not a complete basis here of the system, but it doesn't matter so much. It's still, like the most active part of the system is there. So this is why I use this expansion.
Any other question?
To couple the photon to the, say, tunnel barrier to the hybridization rather than to the density. I don't immediately.
That's exactly this term here.
Oh, okay. So
this is, you see, this is a hopping term now, which is depends on the photonic field. Absolutely. Yeah, I cross it because these are weaker effects, but that's exactly this term. Yeah. You could have off-diagonal terms. Yeah, here you could have an off-diagonal term, which is here. I cross because this is an overlap here. So this is an overlap of the wave functions. This is a matrix element of the wave function. So if the orbitals are very much localized, this is a much smaller term than this one. Well, yes, if the screening, for example, I think in 2DX, in semiconductors, if the barrier is defined electrostatically, then of course the overlap can be bigger, and the V perpendicular here can penetrate further into the orbitals, and therefore the matrix element can get bigger. I guess it's always possible to boost this term. It's just that experimentally nobody has ever measured the effect of this term. That's more why and then it's reasonable why it's difficult to measure, because usually it's an overlap, so which is smaller.
So I guess the H naught also you write in a similar basis, and that has like it's a regular hopping Hamiltonian, is it?
Oh yes, exactly. So we will absolutely. So it's a hopping Hamiltonian, and so for the single dot, it's just epsilon d d dagger d, and for the two dots, it's going to be there will be the hopping term and the local part of the Hamiltonian.
And the leads are like at thermal equilibrium at some chemical potential.
This is we assume that the leads are some thermal equilibrium.
Okay, any other question? Okay.
Sir, I have two questions. In the one question means in writing the generalized Hamiltonian, you have not taken account the electron-phonon interaction or something like phonon-photon interaction. So it can lead some new things or.
Well, yes. So you're absolutely right. So I specify only. I just essentially use. Only a coupling to one kind of bosonic mode. You could, of course, imagine to generalize this to a coupling to different kinds of bosonic modes. So you could say, okay, the electronic system is coupled to phonons, which is also coupled to photons. And then, of course, this can lead to cross-coupling between the phonons and the photons. That's true, yeah. So you could generalize this straightforwardly, I think, to this situation. The hard-wall boundary. So you will see this afternoon or maybe tomorrow. So this is but okay, no, you can always prepare the hard-wall boundary. For example, if you have a semi-conducting quantum dot, you just can put one of the plunger gates such that the coupling here, there will be always a reservoir somewhere, but you can say that the coupling to this reservoir will be in the kilohertz range or even lower. And therefore, this will essentially be a hard-wall boundary. So in our case, we will do this differently. We'll put a superconducting gap here. That's it.